So in this lesson, we're going to focus on how to prove triangles similar. And thus far, we have only talked about using angle-angle similarity to prove triangles similar. With angle-angle similarity, we've found that if two angles of one triangle are congruent to two angles of another triangle, then those triangles are similar. So in this case, on the far right, we have angle A similar to or congruent to angle B, and angle C and F are also congruent. So that's two angles. That's enough to call these triangles similar. So when we write that down and say angle A is congruent to angle B, C is congruent to F, therefore the two triangles are going to be similar based on angle-angle similarity. Okay, similar, not congruent. And we can write a similarity statement by saying triangle ABC is similar to triangle DEF. So we have the kinds of questions that we have with this include then deciding whether two triangles are similar when we're given some angles. So if we look at our first example here, angle T is 105 degrees, and we don't know what angle W is, but we see that angle V is 36, as is angle Y. So if angle U was 39 or angle W was 105, we would know that those two triangles are similar by angle-angle similarity. But one pair of angles is not enough to prove that they're similar. So we need to add the 105 and the 36 to get 141, and we would subtract that number from 180 to find out whether we get 39 degrees or not. And it turns out that 180 minus that 141 does equal 39. So the measure of angle U is the same as the measure of angle X. So these two triangles are similar by angle-angle similarity. Some students say, can't I just take 105 plus 36 plus 39 and see if that's equal to 180? And absolutely, that's a perfect strategy. You decide which works best for you. In this next example, we wanted to find out if the triangle PQR and triangle LMN are similar. And we want to explain our reasoning. So the measure of angle P is 63 degrees, and the measure of angle R is 18. So the thing that's missing from this particular example is the pictures. So you can certainly draw the triangles. You don't have to have perfect measures and so forth, but just draw two triangles that appear to be similar, label them, give P a measure of 63, R a measure of 18, L a measure of 63, and M a measure of 97. So we see that 63 and 63 are equal. We have one pair of angles that are congruent. Let's find out if the other pair of angles are going to be congruent. The way to do that is to add the 63 and the 18 and subtract that from 180 to see if we get 97. Well, it turns out that when we take 63 plus 18, we get 81. So 180 minus 81 is 99, and that is not equal to 97. So the two triangles are not similar. Two pairs of angles have to be similar to make the triangle similar. So that works when we have angles given. What if we are shown sides and measures of sides and have to decide if those triangles are similar from that? Well, the side-side-side similarity theorem says that if the measures of corresponding sides of two triangles are proportional, then the triangles are going to be similar. Remember that proportional means that we can write them as fractions, and those fractions should be equal to each other. So when I look at these two triangles, it appears that one is a reflection of another scaled down. So NO appears to be the proportional side with QR, and P would be the proportional side with QS, and OP would be the proportional side with SR. So our proportional statement, our statement of proportionality, would say that if NO over QR is equal to OP over RS, and that's equal to PN or NP over SQ, then those triangles will be similar. We can write a similarity statement. Triangle NOP is similar to triangle QRS. From that, we can decide whether triangles are similar or not when we're given three sides to compare to three other sides. So when you're doing these types of problems, I want you to think about the Goldilocks and the three bears. We want to remember Papa Bear, Mama Bear, and Baby Bear. So we're comparing the smallest triangle to the largest triangle, or the medium-sized triangle to the largest triangle, and trying to decide which one is similar to the largest triangle. So with triangle GHI, I look at this and I ask myself which one appears to be, or which one is the largest side of this triangle. And GI is my Papa Bear, my largest side of my triangle. GH is my Mama Bear because it's the medium-sized side of the triangle, and HI is the Baby Bear. So once I have them listed in order, now I can do the same thing with the largest triangle, triangle JKL. My largest side of that one is 15. That's my Papa Bear of that triangle. My Mama Bear is the 10, and the Baby Bear is the 8. So when I'm setting up proportional statements to decide if these are fractions, to decide if these are proportional or not, if I go from the large triangle to the small triangle, I want to start with the large triangle's Papa Bear and put the small triangle's Papa Bear beneath, and ask myself, does that equal the large triangle's Mama Bear, the medium-sized side, versus the small triangle's medium-sized side of 6? And is that equal to the Baby Bears, the 8 over the 4? Large triangle's Baby Bear, the small triangle's Baby Bear. Well, I notice that this one reduces to 2, but 10 over 6 and 15 over 11 do not reduce to 2. So I can say that no, triangle GHI is not similar to triangle JKL. So let's compare the very large triangle to the smallest triangle. My Papa Bear is my 3, my Mama Bear is 2, and my Baby Bear is 1.6. So now let's check and see. Again, the 15, 10, and 8, if I write them from smallest to largest, how does that compare with the largest, again, to the medium size 2, to the smallest one of 1.6? Are these equal? So 15 divided by 3 reduces to 5. 10 divided by 2 is 5. And 8 divided by 1.6 is also going to be 5. Okay? So we know that triangle TUV is similar to triangle JKL. Papa Bear, Mama Bear, Baby Bear helps you set them up in the right order so that you can check if the proportions are correct or not, are equal or not. Okay, so next example is also a side-side-side similarity example. They tell us that triangle JKL is similar to triangle GHI. That means that the sides have to be proportional. So you have to look at these and decide which one appears to be the longest side. We're going to call that our Papa Bear. And it may not be the longest side when it's all said and done, but as long as we're writing our proportional statements in the correct order, we'll be fine. So if we look at this and decide that the 30 appears to be the longest side, JL is listed first and last, so that would have to be the proportional side to GI, the corresponding side of GI. And if we decide that the 3x times x minus, the quantity x minus 6 is the medium-sized one, then we would have to say the 6 is also the medium-sized one. So we're going to label those the Mama Bears, because KL and HI are listed in order as the second and third letters or angles of our triangle. And then finally, our Baby Bears would be the 15 and the 5. So now when we set up our proportional statements, we would have 15 over 5 if we go from small triangle to large, Baby Bear. is equal to, our mama bears would be the 6 and the 3 times the quantity x minus 6, and our papa bears would be the x minus 2 and the 30. So now we have three proportional statements, and we have variables in two of them. So we don't want to work with the ones that have 2 in them. So the easiest one to work with, most likely, is going to be this 5 over 15, because we know the baby bears in both. And this last one, the x minus 2 over 30, because there's less complex fraction. So when we cross multiply here, the 5 times the 30 equals the 15 times, and we have to make sure we put this in parentheses, the x minus 2, all of that has to be multiplied by the 15. So 5 times 30, 5 times 3 is 15, and add my 0. And 15 times x gives me 15x. 15 times a negative 2 is a negative 30. So we add 30 to both sides to get our numbers to one side, variables to the other, and we get 180 is 15x. When we divide by 15, we find out that x is equal to 12. We can test ourselves or check ourselves to make sure that it's right by using our third fraction here. We can take the 6 and we can divide it by 3 times 12 minus 6 as our check. 12 minus 6 is in parentheses. We're doing that first. We'll get a positive 6, and 3 times 6 is 18. So does 6 over 18 reduce to the same thing that 5 over 15 does? 6 and 18 have a 3 in common, so we get 1/3, and 1/3 is also equal to 5/15. So we know that it checks. So x is equal to 12. So a third way to prove two triangles are similar is to use the side angle side similarity theorem. The side angle side similarity theorem says that if two sides of one triangle are proportional to the corresponding sides of another side of the triangle, so now we only have to have two sides, not all three, and the included angles of those two triangles are congruent, then those triangles are similar. So because we want the included angles to be congruent, that means those have to be the angles that are between those sides. Included means between, next to, or part of. And so we want those two sides to be the sides that help make that angle. So in this example, angle J and angle G are given as congruent. So we want the side JK to be proportional to GH as JL is to GI. So if JK over GH equals JL over GI, and the angle is that's between them, angle J is congruent to angle G, then we can write a similarity statement. Triangle JKL is similar to triangle GHI. We can use that knowledge to decide if triangles are similar or not. So here I see two pairs of sides that have measures, and I see a pair of angles that have measures. So it's not two angles, so we can't use angle-angle similarity, and it's not three sides that I can compare, so I can't use side-side-side similarity. I will have to use side-angle side similarity. So I ask myself, are the sides proportional, and is it the included angle? When I look at these, the 15 is the larger of the two, and the 12 is the larger of the two. So I would compare 15 to 12, and I would compare the 10 to the 8. But 15 over 12, they both have a 3 in common. That reduces to 5/4. 10/8 has a 2 in common. That reduces to 5/4 as well. So we have sides, two pairs of sides that are proportional. But the most important thing to realize with side angle side is we have to be able to have the included angle congruent. So when I look at angle J and angle F, I have to ask myself if it's at the included angle between the sides that I have given. And angle J, is not made by those two sides. It is an excluded angle. It's outside of those. To make this work by side angle side, I would have needed angle I and angle E to be congruent, because those are the angles that are between the sides that are given. So this is not true, because the sides have to be proportional and the angle must be the included angle. The sides being proportional is not enough. It has to be the angle that's between the two. Last example says decide if these triangles are similar, and if so, write a similarity statement and justify your answer. So I see a triangle nested or embedded within a triangle. So if I want to break those two triangles apart, I can say there's a smaller triangle and a larger triangle. Try to make them look similar. That smaller triangle has sides that are 8 and 12. The larger triangle has sides that are 10 if I add my 8 and 2, and 15 if I add my 12 and 3. And notice that angle K is a part of both triangles, and that is the included angle between those two triangles. So all that's left is to decide whether or not the sides are proportional. So I would take the 8 over the 10 and ask myself if that's equal to the 12 over the 15. So we can cross multiply to see if we get the same result. We can divide to see if we get the same result, or we can simplify to see if they're the same. And 8 over 10 does equal 12 over 15. K is in both triangles, and it is the included angle. So our similarity statement is going to say triangle MKN is similar to triangle LKP by side angle side similarity.